We're continuing our analysis to obtain expressions for the amount or fraction of monomer 1 and monomer 2 that are present in copolymers that are synthesized using free radical copolymerization. And when we left off last, we obtained an expression like this for the ratio of the mole fraction of monomer 1 to the mole fraction of monomer 2 in the copolymer. Notice that this contains the concentrations of monomer 1 and monomer 2 in our reaction mix, but it also contains this term, which involves the concentrations of active chains that end in monomer 1 and active chains that end in monomer 2. So the concentration of monomer 1 and monomer 2 we know because we make the reaction mix. We know how much we're adding, but these concentrations of active chains are not as convenient to deal with. We don't really know what those are at a given time in the reaction. But if you remember, earlier in our analysis, we invoked something called the steady state assumption. And the steady state assumption basically said that the concentration or the amount of chains, active chains that end in monomer 1 and active chains that end in monomer 2 is essentially constant during most of the polymerization process. In other words, the rate of change of concentration of chains that end in monomer 1 and chains that end in monomer 2, active chains, is equal to 0. And we use that to express this ratio of the active chain concentrations in terms of a ratio of the concentrations of monomers 1 and 2 in the reaction mix times this ratio of rate constants. So we can substitute that in to our expression for this ratio of the mole fractions of monomer 1 and 2 in the copolymer and obtain an expression like this. So now this is convenient because now we've obtained an expression for monomer 1 and monomer 2 in the copolymer, or the copolymer composition, in terms of what we add to the feed, or the concentrations of monomer 1 and 2 in the reaction mix, times these rate constants that tell us something about how the reaction progresses. This is what we want, but we can simplify it further into a more convenient form. And one step to doing that is to divide by this product K21 times M2. And so when we multiply that through, apply it to all these terms, we end up with this expression. And notice that this involves ratios of monomer 1 to monomer 2 and ratios of these rate constants. So now we can define something called a reactivity ratio, which is basically an expression of these ratios of these rate constants that appear in this equation. So in other words, little r1, or reactivity ratio 1, is K11 over K12, and reactivity ratio 2 is K22 over K21. And basically you can see that this is expressing the ratio of the rate at which the same monomer is added to a growing chain versus the cross-reaction rate, or the rate at which the other monomer is added to a chain that ends in one monomer. We can substitute that in, and we end up with this expression here in terms of the reactivity ratios. Now, we can also adjust this a little bit further by, instead of expressing directly these concentrations of M1 and M2, we can express them as also mole fractions of M1 and M2, but in the feed or in the reaction mix. So remember, capital F1 and capital F2 refer to the mole fractions or the fractional quantity of monomer 1 and 2 in the copolymer, or the product. Little f1 and little f2 are defined to represent the relative fractions of monomer 1 and 2 in the reaction mix or in the feed. So I think you can see that if I take the ratio of little f1 to little f2, then I get m1 over m2. And that's the term that I have involved in this equation. So then I can substitute in this ratio of these mole fractions in the feed and obtain the following expression. This tells us the relative amounts of monomer 1 and 2 that are present in the copolymer or the product relative to how much of monomer 1 and 2 we added into the reaction mix or into the feed. So I can simplify this a little bit more by multiplying the numerator and denominator by this ratio f2 over f1, little f2 over little f1, to obtain this expression. And then finally, I'm going to rewrite it so that everything is expressed in terms of one monomer. In particular, I'm going to choose monomer 1. And we can do that because notice that big F and little f are mole fractions. So since they're fractional quantities, F1 and F2 equal 100% or 1 in terms of their fractional quantity. So in other words, I can express the mole fraction of monomer 2 as 1 minus the mole fraction of monomer 1. So I can express one in terms of the other, and that allows me to then rewrite this expression in a form that involves only one of these species. So if I rewrite this in terms of only monomer 1, then I have the following expression below. F1 over 1 minus F1 equals these terms that involve reactivity ratios and the mole fraction of monomer 1 in the feed. This is an important relationship. This is called the copolymer equation, and this gives us exactly what we want. This tells us how the composition of the copolymer in terms of monomer 1 and 2 is dictated by how much of monomer 1 and 2 we add to the feed and what the relative rate constants are associated with addition of these monomers to the copolymer during propagation.